So it appears that I have to live in the middle of the second hour. So what we will do today, I'll first give in 45 minutes some sort of crash course on complex analysis, listing all the things we will need from general complex analysis, just in case. And then formulate a few things about discrete harmonic functions, which we are already given as exercises, and then in the remaining 2 hours, you will prove them yourselves with the help of Misha. Now, so the, let's say, crash course on complex analysis. So there are so the main object, so we deal with functions f from omega, which is domain in complex plane to complex plane, and we say that f is analytic, or people use the word holomorphic, or people used to use the word regular. If you read old books, they use the word regular. If for every z0 in omega, there exists a complex derivative, f prime of z0, which is the limit f of z0 plus epsilon minus f of z0 as over epsilon, f epsilon tends to 0. Now this is basically says that there exists a complex derivative. It's a much stronger property than saying that there are two real derivatives fx and fy, because it implies some relation between them. And there are, it's sort of very special. You use that complex numbers I filled and have some nice two-dimensional real one-dimensional structure. So there is a multiplication by I, and there are similar objects in higher dimensions, like C2, C3, but they are not as nice as in one-dimensional complex world. And the reason why there are several words used, so now people say that mathematicians use analytic and physicist holomorphic, or the other way around, I can never remember. But originally just analytic, holomorphic, or regular were different definitions. And it's a basic theorem, one of the first theorem in complex analysis textbook, that the definitions are equivalent. But originally what people meant, so this is, let's say, a theorem that the following are equivalent. And the properties are so that there exists complex derivative f prime. So this means with the following definition that f is holomorphic, or equivalently f is a homomorphic of omega. And now the other way is to rewrite this in terms of partial derivatives with respect to x and y. So you write that f is c1 of omega. So there are derivatives with respect to x and y, and then there are f you write as u plus iv, two functions, and then there are Cauchy-Riemann equations. Which I never can remember the sign. Ux is equal to vy, and uy is equal to minus vx. So those are derivatives. So that's often how things are defined. So by the way, what happens if I confuse the sign and put the sign in the wrong place? What happens? What is the result of this?
Anti-homomorphic.
Sorry?
It will be anti-holomorphic.
Yeah, what does it mean, anti-holomorphic?
It was space.
Well, yeah, the correct thing is that we change orientation of the plane. So when you choose real and imaginary part, you choose x and y axis is like that. So x goes to the right and y is the first counterclockwise. And if you do the other way around, then it's the same as analytic in this basis, that y is clockwise. So there is this symmetry in the plane, there is an orientation you can choose. It doesn't really change a thing, but so once people decided that complex numbers multiplication by I is rotation counterclockwise by 90 degrees. But you can declare it to be clockwise, and then you would have the same equations, but you just confuse the sign.
But you have problems when you will take compositions of two holomorphic functions in new definition. It will be not holomorphic probably.
Well, it's well, yes. Well, okay. So you have to be careful what you do. Yeah. That it's that is right. But basically, okay. So there are two planes here. There is xy plane and there is uv plane. And then there is a question how you define orientations in both. Yeah. So yes, you are right in that sense. So there are actually two sort of binary things. What is the orientation of xy? What is the orientation of uv? Okay. Now there is an equivalent definition. Is that there is a primitive f, function f, which is there is a primitive f on omega, which is holomorphic. So there is a primitive in holomorphic omega, and f prime is equal to f. So there exists a function whose derivative is f. Well, then automatically it's holomorphic because it has derivative. There is a primitive f. So by f prime I mean complex derivative. So it's means automatically that f is holomorphic. Then there is that f is analytic. So by analytic, people mean that there is a power series expansion around every point. Near every z0, f of z0 plus epsilon can be written as a sum of ak epsilon to the power k, which converges for sufficiently small epsilon. For absolute value of epsilon smaller than r, where r, well, it will be actually it can be chosen to be distance to the boundary. So that immediately implies that f is C infinity in omega. So the previous definitions, they only asked for C1, but it automatically C infinity. So it's very different from real numbers. If you have a function with a derivative on real line, it doesn't, by no means, it implies that it has all the other derivatives. So it's rather a complicated thing. And let me say that the other thing that, so for every contractible contour gamma inside omega. Contractible, I mean that omega might have a hole, so I don't want, I want only contours which don't go around the hole. So contour integral of f over gamma is equal to 0. Now, what is the contour integral of f over gamma? So this is so let's say 0. So this is by definition is the integral, the length of gamma, f of z dz. So this is just, you understand, as a Riemann integral, our function is continuous. So let's say for every contractible contour, well, there is a question which contours we want. So for us it's enough for this, so it will be true for any contour of finite length, any rectifiable. but it's enough to check it for all circles, or all squares, doesn't matter. And the reason is that, for example, this contour you can write as the sum of square contours in this way. So you just take, well, okay, that's a bad start, but you start taking integrals over such contours counterclockwise. And then what happens if they touch, these two parts cancel because they come with different sign. These two parts cancel when they come with different sign. These two parts cancel. So from squares I can easily get polygons. And by such polygons I can easily approximate my contour with arbitrary precision. So it doesn't really matter. So maybe here for every rectifiable or rectangular, it doesn't matter. So this is just Riemann integral. So this is the limit of the sum f of zj plus 1 minus f of zj times zj plus 1 minus zj, where you partition this contour into small pieces. So the last one actually has a name, so this is called Moreira theorem, the last one. So I'm not going to prove this. There are some obvious implications. Basically, if f is analytic, obviously it will have complex derivative. It's just the first coefficient in this series. If f is analytic, you can also from that get primitive by summing by just integrating formally this series and showing that it's summable. For example, number 5 is called a theorem because it's more complicated to prove. So if you haven't seen it before, it's actually a very good and a bit tough exercise. But basically what you do to show that integral over the rectangular contour is equal to 0, you split this contour into 4. And then you split each contour into 4 again, and so on and so on and so on. But then what you observe is that if the contour is very, very small, the integral, the length of this contour will be very, very small. Why? Because f has a complex derivative. So you can write, like if you have integral of a small contour, what is, if z0 is at the center, what is f of z0 plus epsilon? It's f of z0 plus epsilon f prime of z0 plus small order terms. So what you can see is that you can just check manually that these two terms integrate to 0 because it's a constant. Contour integral of constant is 0. Contour integral of epsilon is 0. And the rest will be smaller than the size of this squared, and that sort of helps. So it's enough actually to check it for that integral of 1 is 0 and integral of z is 0, and then split everything into small things. On the other way, the other way around is that if contour integrals are 0, it means that when you integrate function from a to b via two different paths, you get the same result. Because the difference between these two results is just integral of this plus integral of that. So this is the difference, and it's contour integral. So integral along the path is well defined, independent of the path, and this gives you the primitive. So from that you get the primitive. So this is, if you have not seen this, we can talk later, put it in, you ask me, show myself, I'll put it into the exercises, but we'll also see how this arises in the discrete setting, which is more important for us. So those are the properties. Now, those are the equivalent definitions. Now, a few properties we need. Well, I mean, first, property 0, that we don't have to do it with the values in a plane. We can do it with the values in a complex sphere. So we just we rotate the complex. If we hit infinity, we rotate it so complex sphere so that infinity is not infinity but some finite point. So we can define functions f omega into complex sphere, and they are called meromorphic. So the question is only how you define derivatives if you hit near infinity, and the way you do it, you just rotate infinite points so that it becomes finite point and write everything in new coordinates. So that's so that actually we won't need, but just in case. Now basically the main thing is the Cauchy formula, and this is the thing which allows to prove that if a function which allows to deduce that it is analytic, for example, that it says that if you have a contour gamma, so if z inside contour gamma, then f of z is equal to 1 over 2 pi I contour integral over this contour gamma f of zeta over zeta minus z d zeta.
What does it mean to be inside if you're working on the sphere?
It's a good question. Yeah, well, it's maybe the next property. So look, well, this is a sphere. So I did not allow so far domain to be the whole sphere, but there are basically two things. So let's say. So this is for f only holomorphic. So it has values in a plane, not finite. So what first happens is that if you put z on this side, then you have to orient it counterclockwise. If you put that side, it's also inside, you have to orient it the other way around, counterclockwise around this point, just rotate the point. But there is a trick that suppose that your function is analytic in the full sphere. If it's analytic in the full sphere, it's Liouville theorem, but it's actually constant. So the only function which is analytic in the full sphere and finite is a constant. So we will see it's also for harmonic functions. So for harmonic functions, the only harmonic function in the whole plane, so the only bounded harmonic function in the whole plane is constant. So that's, or the only harmonic function on the sphere is constant. So it's, so okay, so that question actually doesn't arise. So there is only trivial function for that. Okay, so why this does not contradict contour integrals? Because this function is no longer holomorphic. It has a pole. It is actually meromorphic. It has one singularity. And basically what you can do, you can factor out this singularity and leave holomorphic function. So then, so basically you write something like f of z over zeta minus z. So you sort of take away something like that, and the rest is holomorphic. So the holomorphic rest will have zero contour integral. So it's enough just to analyze what will be the contour integral of such a guy. And it doesn't depend on a contour. You can contract the contour just by the same property that contour integrals are zero. So basically, if you have only one singularity, you don't care whether it's this contour or this contour, because you can move them outside singularity. So you have to integrate this along very small contour that you can just do by hands. If it's a, so this is if you haven't seen it. But then you see this can be differentiated. So for example, you can write f prime 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 z is the third derivative of this guy. So the third derivative of this guy will be minus 1 over 2 pi I f of zeta zeta minus z to the power 4 d zeta integral. And when we get to the power 4, we get to 3, so it's power 6. So this is an example. We differentiate thrice. And what it allows you to do, if you have estimate on how big f is on the boundary of a contour, you get estimate on the third derivative inside. And very well on the hundredths derivatives or 200ths. So essentially this means that easily they get in a Sobolev class or any other smooth class, because you get, so this, the remark is that estimate f prime, f prime prime, f prime prime prime, etc. in terms of f on gamma. So this is very, very important property, the Cauchy formula. Now, what else we will need? So the holomorphic omega is complete in topology of uniform convergence, in uniform convergence topology. It's obviously not compact because you can take a sequence of constants, constant 1, constant 2, constant 3, and it diverges away to infinity. And there is a special different notion of normal families where you take some subset of holomorphic functions and you discuss whether it's compact or not. For example, bounded functions are compact in uniform convergence topology on small subsets because of this formula. Because if functions are bounded, then you get bounds on their derivative, so they will be uniformly continuous. So they will be compact on a small subset. So this is a small remark. So it's the set of f in holomorphic of omega. F absolute value of f is smaller than constant is compact in, well, again, let's say in C of omega 1 where any omega 1 inside omega. So if you just step a little bit aside from the boundary, this formula allows you, writing integral along some curve following the boundary, allows you to get here inside estimates, so you get compact. So this is from Cauchy formula. So this is actually a very nice property. So there is a whole theory, so it's usually called theory of Montel's normal families. It allows you, we will use it, but when we come to use it, I will just do it at that place and time. So for example, function f which is bounded, functions f which are bounded, they form a compact set on slightly smaller domain. Again, it's very different from Leo-Rhine. If you have differentiable functions which are bounded, this set is not compact because they can have very big models of continuity, arbitrarily big. But here, the fact that it's bounded by Cauchy formula gives you an estimate on models of continuity. So everything is nice, and you can pass to subsequence. But then there are very interesting things because there are conformal maps from half plane to a disk. So if function has values in half plane, then you can get from it a function with the values in a disk. So from that you can deduce that if function has real part bounded, it also gives you a compactness. And there are more interesting things if there are maps to a disk from a plane emitting 3 points. So this is these pictures you have seen of the modular group. So well, we'll speak about it later. So if if you take functions which emit 3 values, you also get compactness. So it's actually much weaker property. It's enough that function admits 3 values. For example, infinity, 0, and 1 on the sphere. But we'll come to this later. So it's a separate question. So for us it is important because we will a few times we will work by compactness. We will need to show that sequence of functions has a certain limit, and first we by compactness get subsequential limits. Now what I forgot to say, which was actually supposed to be property 0, but let's say property 3, which is easy. So if fg are holomorphic, then f plus minus g, alpha f times g are holomorphic, and f over g is holomorphic whenever G is non-zero. So that's an easy property. Then there is maximum principle. So basically, if you have again a contour gamma, so max with supremum f inside gamma is no more than supremum f on gamma. And then there is mean value property. So f of z0 is the integral over the, let's say, integral the length of the circle. So let's say absolute value of epsilon is equal to r. F of z0 plus epsilon, the epsilon, and the length of the circle is 2 pi, so 2 pi r. And the last property we will need, which allows sometimes to check that function is actually a conformal map. So this is the so-called argument principle. So suppose that z is so fix some point u0. Then number of z inside contour gamma such that f of z is equal to u0. So you have a contour gamma, you have a point, and you want to see. So there is a function f. Which maps it somewhere, and you want to see how many times the value 0 is taken inside this contour gamma. So you map the contour gamma, and then you check how many times it goes around u0. So it's the number of turns with sign f of gamma makes around u0. So basically what you mean by number of turns is that you put an arrow here and then you start moving the point. And you have this arrow and you just check how many turns it makes, but it can go back and forth. So for example, you can imagine that you have here a screw which is going into the plane, and with a screwdriver you sort of start going around the corner. So when you go left you unscrew the screw, when you go right you screw it back, and then after you make this thing many times, you make some full number of turns, either 0 or 1 or -1, etc. So basically this says that if you have 0 turns, there are 0 solutions. If you have 2 turns, there are 2 solutions, and so on. And the negative number of turns you can't have at all unless you have meromorphic function, but that we don't deal with at all. So maybe I should say that this is counting. So this counting the valency of the root. So if the root is of order 2, then it counts twice. Now, so that's basically everything we'll need for homomorphic functions. Now they're intimately related with harmonic functions, and so we say definition that H is harmonic in omega, so it's harmonic, if Laplacian of h, which is h derivative with respect to x, derivative with respect to y, is equal to 0. Now, you don't see it when written in coordinates here, or when you write Cauchy-Riemann equations, you don't see immediately that they're actually rotationally invariant. With analytic functions, it's clear when you write that there is a complex derivative that you don't care whether x, y go like this, like that. Here it's not immediately clear, but it's an easy exercise that if you change coordinates, you get the same operator. So essentially, this is the only first order operator so this operator that Cauchy-Riemann equations, you often write that there is d bar of f operator, d bar of f is equal to 0. Yeah, I haven't actually written this. You can write the definition number 6, that d bar of f is equal to 0. And so similarly, the only second order operator is this one. And there is something which is very special for the dimension 2, so harmonic functions you can do in any dimension. You can do in dimension 3 or 4 or 5, etc. They will be just as nice. But they're slightly easier to work with in dimension 2. And theorem says that if f is equal to, let's say, u plus iv is holomorphic, then u and v are harmonic. And this is just an easy check using Cauchy-Riemann equations or using the derivative. On the other hand, if u is harmonic in omega and omega has no holes simply connected, then there exists u tilde, which is called harmonic conjugate, such that f, which is u plus I u tilde, is holomorphic. So this immediately implies that harmonic functions have very nice property that they are infinitely differentiable. Yeah, harmonic, by the way, I only asked that h is C2 of omega. So I only asked what is needed to write this identity, but it automatically means that it's C infinity. So this is also true in R3, but you cannot use analytic functions to prove it anymore. So you have to prove it otherwise. Now let me see what else do I need to do. Okay. So now there is another thing. So there are so-called conformal maps. So it turns out that many of the analytic functions will need are conformal maps. Yeah, by the way, I forgot here that composition also is holomorphic. Well, whenever it is defined. So, so conformal maps, it's a function f from, let's say, omega to c, which is holomorphic and injective. So it's 1 to 1. So it's, well, let's say omega 1 to omega 2 in C homomorphic 1 to 1. So the other words which I use are univalent. Again, there are several definitions, and there are several words. And also, still people often use the German word schlicht. So there are some books where they say schlicht functions. though it's less rare. So there are equivalent definitions. Equivalently, f belongs to C1 and preserves angles. What does it mean? So I take two curves and I map them by f. If f is C1, then the curves will still have tangents. So the tangents will still be well defined, and then the angle is preserved. So it turns out that it's enough for a map to check this property. Or f is C1 preserves small circles, well, rather infinitesimal. So again, small circle, if it's C1, it will go, well, it might possibly go to an ellipsis, so it might be stretched in one direction. So what I say by preserved circles, that to the first order it's a circle. So there is no ellipsis, it's not stretched in one direction, it's just so that locally, it basically means that locally it is rotation and uniform stretching. So there is a Riemann uniformization theorem which everyone should know. So there is a Riemann uniformization which says that for any simply connected omega, so any simply can be conformally mapped either to complex sphere or to complex plane or to unit disk, which is denoted by D. Now, of course, I think that, so there is, let's say, a note. So if omega is inside complex plane, then it cannot be mapped on a complex sphere already, because it's just if it's missing at least one point, it is mapped here. So essentially, if omega is C and omega not equal to C, then omega mapped to D. So the interesting thing for us is just any bounded simply connected map domain can be mapped to D. Now, how this is proved? So Riemann did not prove it, so he proved it, but with a mistake, more or less. He made the same inaccuracy as Newton proving that orbits are elliptic, because he minimized some functional and then assumed that it has a minimizer, and you have to prove it, as we know now. And it's not clear who first proved it, maybe Kirby, maybe Osgood in the United States, but there are several proofs of it. So usually you minimize or maximize something, so there are several proofs. For example, you can take, if you take omega and you take disk, take all conformal maps, f from omega inside disk, not necessarily into the disk, not necessarily covering the disk, but inside disk. So one has to show first that such maps exist, which is non-trivial if omega is not a bounded domain. If it's bounded, it's trivial, you just shrink it. If it's unbounded. And then maximize among those, maximize f prime of Z0. And that will give you a map onto a disk, because if it doesn't cover the whole disk, you can stretch it a little bit. Or equivalently, you can take all holomorphic functions f omega onto D, and then minimize what? I'm not sure. I think you have to minimize just the area integral of f prime squared, something like that. Yes. That sort of thing. Yeah. So there are several different proofs. So we'll do a proof using discrete analytic functions, a proof of sorts. And this is related to the Dirichlet problem for harmonic functions. So Dirichlet problem for harmonic functions. So this says that if you have domain omega, let's say with smooth boundary, so I will simplify the thing, smooth boundary gamma equal to boundary of omega. Yeah, so I often write that we have contour integrals, and quite often you want to take contour integral along the boundary of domain where your function is defined. So usually what you do, you step epsilon away, so that you can, because domain might be fractal or something, so you step epsilon away, draw a nice contour, and take integral. So gamma is d omega, and suppose that, let's say, what are the other nice, g belongs to, g is a continuous function on gamma. Then there is unique function h, which is continuous in the closed domain omega, so that h on gamma is equal to g, and Laplacian of h is 0 inside. So there is a unique harmonic function with given boundary values. So this, for example, if you have a room, and you know the boundary temperature on the walls of this room, and everything is stationary, so after a long time, the temperature inside the room will be harmonic. So because at every point it will be basically mean value of temperatures nearby. So harmonic functions obviously also have mean value property because they are real parts of analytic functions which have mean value property. So this is how physics solves this problem. So if you have some closed volume and you put temperature on the boundary, then inside it will satisfy this. So there are several different proofs. So the analytic proof is take all h which are in C of omega hat, minimize integral gradient of h squared over omega. So this is the energy, and you then can show that this means that h is harmonic. So I'm a bit here unrigorous because, well, for arbitrary function h, this might be not defined or infinite. You might have no derivatives. So I sort of indirectly imply that such functions with this finite exist. And then there is a probabilistic way to do it. Probabilistic way to do it is the following. So start Brownian motion in the plane from point Z. Let tau be the supremum of times t, supremum of t, so that bt is inside omega. So it's the exit time from omega. So basically what you do, you draw Brownian motion, eventually it will hit the boundary, time tau. So what is true, that you can take h of z to be the expectation of g at b tau. So you run the Brownian motion till it hits the boundary, you sample function g there, and you take expectation. So this is approach of Kokutani. So this is Japanese mathematician Shizuo Kokutani. Shizuo, I don't remember. Yeah. He worked at Yale and in Japan. So this theorem allegedly he proved. So he was extradited from the United States when the war started. And actually it was rather sad because his wife was also Japanese, but she already got citizenship. So she was interned into a camp and spent 5 years of the war in a camp. And he was put on a boat back to Japan. So he proved this theorem on a boat. Okay, so and then they reunited 6 years later. Okay, so that's the probabilistic proof. I think that's more or less what. By the way, that gives us this gives us the proof of Riemann uniformization. So how this gives us the proof of Riemann uniformization? So I was a bit cautious here, so I only formulated it for continuous boundary data. But in principle, you can certainly do a few jumps. So this will work in more detail with discrete analytic functions. So proof of Riemann. So let's take domain omega, and let's take G equal to 1 on this arc, and G equal to 0 on the other arc. So there are 2 points A and B. So on arc AB, it's 1, and on arc BA is 0. So solve Dirichlet. So we get function H, which is harmonic in omega. H is equal to 1 on BA. H is equal to 0 on AB. Now, there is harmonic conjugate. There is H tilde, so that F equal to H plus IH tilde is holomorphic. Now, what happens with this function f? So the function f has a real part 0 on this arc. So this arc is mapped to vertical line, just the vertical axis, and 1 on this arc. So those are boundary values. Now what I claim, f is a conformal map. Why? Because 1 to 1 by argument principle. Why is it 1 to 1 by argument principle? Let's go here around the boundary. We have to step epsilon away, but basically let's, I won't do this for lack of time, but when we go around the boundary, what happens is that we start on this arc. So when we go here, we just go in some way around this arc up and down. Then we jump to this arc, go up and down, and then jump back. So we make only one circle around this point. Because we spend some time on this line, then jump, spend some time on this line, then jump. So we make exactly one turn around. To make 2 turns, you need to jump 4 times. But when you jump 2 times, you only make 1 turn. So this is, bless you, conformal map to a strip, and then a strip can be mapped to a disk if you wish. So just, it's an exercise, what is a map of a strip to a disk? We'll work out next time. So this is perhaps the shortest proof. So what are one has to check carefully that this is true, and one has to check, of course, that the Dirichlet problem for harmonic function works. Now Yeah, by the way, so Riemann uniformization theorem, so there is a remark. So the Riemann map to the unit disk is unique up to 3 real parameters. So the automorphisms, conformal automorphisms of the unit disk are the maps which can be written e to the power I theta z minus a, 1 minus a bar z. So there are 3 real parameters, theta and 2 in a. Now this thing gives us a map. So where there are, so I went with the short exercise. Where are 3 parameters in this proof? So what are the degrees of freedom I can do here with this map to a strip? So there should be 3. Find 3 real degrees of freedom.
A, B, and the constant in the...
Yeah, A and B can be chosen. So A is 1 degree of freedom real because I move it in the boundary. B is another. And what's the third one?
The constant in the harmonic quadriad?
Yeah, so you can move it vertically mapped to the strip. So it's H tilde, the harmonic conjugate can be chosen up to a constant. So I forgot maybe to say it, or I haven't forgot, I don't remember because I already erased. But harmonic conjugate is well defined up to a constant. So if you add constant to analytic function, it's still analytic. So you can, if you define harmonic conjugate plus 1 is also harmonic conjugate. So those are where the 3 are hidden. Now let me maybe end with an open problem. So we'll discuss later, well, maybe next time. So how to uniformize multiply connected domains. So if you take domain with 1 hole, you can always map it to an annulus. And there is a unique ratio of, so for a topological annulus, there is a unique R and map to an annulus. This can be easily deduced from Riemann uniformization by just taking covering of this guy. So it's now it's much more difficult if you start doing more holes. So there is a conjecture. So there is a conjecture which is called Kobe conjecture, and it's fairly famous conjecture Kobe, that for any omega there is uniformization such that all components of boundary of omega are mapped to circles of points. So basically, if you have domain, there are many holes. There might be uncountably many holes, that's why you need points. So it's mapped to something which looks like this. Maybe counter set. So the theorem, basically the best known theorem which I can formulate in 15 seconds is surprisingly due to a person who played important role in this subject. So it's he and Schramm. So Schramm did this before he got interested, where he invented SLE. So they were, I think, postdocs with he in San Diego, and they wrote about 5-6 papers. So this is true for countable cardinality of d omega. So if d omega has countably many components, this is known. For uncountably, it's not known. It's a big open problem. And maybe it's not logical to ask. So what is known? There is a theorem which is much much older, so Schiffer it's about 1930s. So there is a map, so always there is a map where when all boundary components are mapped to horizontal intervals. So you can always map it to, well, let's say we cover infinity also, and we take like the whole plane minus number of maybe point intervals. So that you can always do. And the difference why this is easier is that you can do by just maximizing the one parameter. It's actually you have to write expansion at infinity, and you maximize the real part of second coefficient, and then you get this map. But it's very easy to maximize something to get one component to be a disk. That's what Riemann uniformization theorem does. But when you make one component a disk, the other components, they sort of collapse and become no longer disks. So here there is no universal thing which you can maximize. And here there is, and it has to do with some sort of conformal and modulus invariance. So this is like a big conjecture. I can say that retrospectively it's very reasonable or important because we have this uniformization is just good enough for all the purposes. But still it's a problem many people try to solve, and it's interesting, would be interesting to see whether it's true or not. Okay, so now we have a break. What then you do, you just discuss everything from the homework assignment, and then what we do next time we prove that uniform spanning tree or loop array random walk, whatever we'll fancy first, has discrete holomorphic functions built in, which allows to calculate certain things. So that we'll do on Friday. Okay, yeah, thank you.